Hi, welcome back. In this video, we're going to talk about how we find eigenvectors. Thus far, we've been talking about how to find eigenvalues, and now we're going to talk about how to find the corresponding eigenvectors. So for our first example, let's find an eigenvector for each eigenvalue of the matrix A, where A is 4, 2 in the first row and 1, 3 in the second row. So I've already used this same matrix in 2 of my other videos, and so we already know the eigenvalues. They're lambda equals 2 and lambda equals 5. To help us out and be a little clearer, we're actually going to label these eigenvalues with indices. So I'll have lambda 1 and lambda 2. So lambda 1 is 2 and lambda 2 is 5. Now our goal is to find the eigenvectors that correspond to these eigenvalues. So remember, an eigenvector will have this property that when we take A times the eigenvector, we should get lambda times the vector. And so we can write this for either lambda 1 or lambda 2. Then we're going to use the modified version of this statement in order to help us find that vector. So we'll write this as A minus lambda 1I times the vector v is equal to the 0 vector, or A minus lambda 2I times the vector is equal to the 0 vector. So using these two statements, we're going to be able to solve for v to find an eigenvector for each eigenvalue. Let's start by looking at our first eigenvalue, lambda 1. So if we take this statement, we are doing our matrix A minus lambda times the identity. And here lambda is 2. So I'm writing my matrix A minus 2 times the identity. That gets multiplied by some vector v, which I'll notate with an x and a y. And this is equal to the 0 vector, 0, 0. So we have this equation here, this matrix equation, and we're just going to work through it to solve for x and y. So let's simplify the matrices in the parentheses. I'm getting 4 minus 2 and 3 minus 2 on the diagonal, with 2 minus 0 and 1 minus 0 in the other positions. So my first row is 4 minus 2, 2 minus 0, and my second row is 1 minus 0, 3 minus 2. This results in the matrix 2, 2 in the first row and 1, 1 in the second row. So you'll notice here that our first row is a multiple of the second row. And this is what should be happening. So by design, the system we've created involving the eigenvectors and the eigenvalues with an infinite amount of solutions. You can think here that we have many possibilities for the eigenvectors. There's not just one eigenvector that corresponds to an eigenvalue. So if we found an eigenvector, we could scale it, and then that would also be an eigenvector because we could scale it again, and we could continue to do that. So we have many options for our answers, and so this makes sense that we're getting a dependent system. So from this system, I'm actually just going to write out the equations and solve. So I can write that we have 2x plus 2y equals 0, and then x plus y equals 0. Now I just need to solve in order to find my vector v. So for the first equation, I can do 2x equals negative 2y, and then divide by 2, so I'm getting x equals negative y, or this same answer becomes clearer in the second equation, where I just have x equals negative y. Okay, so what we've found is that our eigenvectors have the form negative y, y for any real valued y. So this could look like negative 1, 1 if I use 1 as my y. It could be negative 3, 3 when I use 3 as my y. It could be 1, negative 1. It could be 7, negative 7, etc. So it's just any vector that has this form. And remember, these are the eigenvectors for lambda 1, which was 2. So okay, we've solved this, but let's just take a moment to make sure we understand an interpretation of what's going on here. So this tells us that the matrix A will take any vector of the form negative y, y, where y is a real value, and it's going to scale it by 2. So it might do something totally different to different vectors, but if the vector has the form negative y, y, the matrix A is going to simply scale it by 2 when it's applied to that vector. Okay, so let's repeat this process for the second eigenvalue. So this work is going to look familiar. We're going to do A minus lambda I times our vector, and that's going to be equal to the 0 vector. Here, my lambda is 5. So when I put these things together, I'm subtracting 5 from the terms on the diagonal, and then just subtracting 0 from the other ones. And when I simplify, I end up with -1, 2 in the first row, and 1, -2 in the second row. So again, we can see that one of these rows is a multiple of the other one. This makes sense. We designed it this way. And so when we write out our equations, we're going to be getting the same answer for both. So I'm getting -x plus 2y equals 0, and x minus 2y equals 0. From this, I'm getting 2y equals x in the first equation if I just move things around, and then x equals 2y in the second equation. Doesn't really matter which one you can use whichever one you want, we're getting the same answer. So this is what we're going to use to write our general form of the eigenvector. So our eigenvectors are going to be of the form 2y, y, for any y in R. And so this might look like the vector 2, 1, if I choose 1 for y. It might look like 4, 2, if I choose 2 for y. It could look like -2, -1, -6, -3, etc. So any vector of this form is going to work as an eigenvector for the eigenvalue 5. So we've solved this, but let's make sure we stop for a second to interpret it. So what this means is that the matrix A takes any vector of this form where we have 2y, y, and it's going to scale it by 5. So any vector that looks like this, when we apply A to it, what A does is it simply scales it by 5. Other vectors that look different will have different transformations, but when we take A with these types of vectors, we get the specific result, which is that it gets scaled by 5. All right, let's repeat this with another example. Let's find an eigenvector for each eigenvalue of the matrix B, where B is 2, 1 in the first row and -1, 4 in the second row. So for this matrix, we don't have the eigenvalues yet, so we're going to need to find those first. So if you'd like, you could pause the video now and practice this on your own. So go ahead and do that if you'd like. You can pause, find the eigenvalues, then do the work to find the eigenvectors, and come back and we'll do it all together. So I'm going to start by finding B minus lambda I. So I take my matrix B, I subtract lambda times the identity. When I do this, I just subtract lambda from the elements on the diagonal. So I do 2 minus lambda, then 1 for my first row, and -1, 4 minus lambda for my second row. Now I'm going to take the determinant of B minus lambda I, which is this matrix I just found. So I'll be taking the determinant, I write these vertical bars to denote that, and I'm getting 2 minus lambda times 4 minus lambda, minus 1 times -1. Now I just need to simplify in order to get a better looking characteristic polynomial. So when I distribute, I'm getting 8 minus 2 lambda minus 4 lambda plus lambda squared, and then I have a plus 1. When I combine like terms, I'm getting lambda squared minus 6 lambda plus 9. And this is my characteristic polynomial for the matrix B. All right, now I just need to solve this by setting the determinant equal to 0, which is finding the roots of my characteristic polynomial. So I have lambda squared minus 6 lambda plus 9 equals 0. And when I factor this, I'm getting lambda minus 3 times lambda minus 3. So the -3 and the -3 make 9 for the multiplication, and they add to -6. Now I just set each of these equal to 0. So I do lambda minus 3 equals to 0, I do it twice, and I'm getting the result that lambda equals 3. So here we have lambda equals 3 as our eigenvalue, it just has multiplicity 2. Alright, so we found our eigenvalues. We have that lambda 1 and lambda 2 are both equal to 3. So really, I guess I would say there's just one eigenvalue. It has multiplicity 2, but there's just the one distinct eigenvalue. Then our ultimate task is to find a corresponding eigenvector to this eigenvalue. So we're starting with the statement that B times the eigenvector equals lambda times that eigenvector, which we can rewrite as B minus lambda I times the eigenvector equals the 0 vector. Now we just substitute in all of our relevant information. So I'm taking the matrix B, I'm subtracting 3, that's our eigenvalue, times the identity matrix. Then I'll multiply by the eigenvector, which is what we're trying to find. I'll use x and y to represent that, and then it's equal to the 0 vector. Now we just need to simplify what's in the parentheses. I'm getting 2 minus 3 and 4 minus 3 on the diagonal, and then 1 minus 0 and negative 1 minus 0 for the other terms, which results in the matrix negative 1, 1, negative 1, 1. Now I'm just going to write out the equations that this represents. It's negative x plus y equals 0, and technically the second row results in the same thing. Negative x plus y equals 0. So solving this, I'm getting y equals x. All of this is just to help us write a general version for our eigenvector. So our eigenvectors for the eigenvalue 3 have the form y, y for any y in R. This could look like 1, 1. That would be when y is equal to 1. It could be 2, 2 when y is equal to 2. It could be negative 1, 5, 5, etc. So any vector that has this form y, y is an eigenvector for the eigenvalue 3. Okay, so let's just interpret this really quick before we finish up. This tells us that the matrix B will take any vector of the form y, y, where y is a real value, and it's going to scale it by 3. So other vectors, when we apply B to it, it's going to do something very different, but B specifically takes vectors of the form y, y and scales them by 3. Alright, so that is how we find eigenvectors that correspond to a specific eigenvalue. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.